In this video today, I'll discuss about the oscillations of loaded spring combination. First, briefly, I'll discuss about that if a single spring is there and a load or a mass is connected to that spring, then its oscillation is in simple harmonic motion. So after we saw that, we will discuss that if two springs are connected in parallel or series end to end, then what will be their time period, or what will be their spring net or combined spring strength, that will basically calculate. So if a spring is there and it is connected to a mass m, then we know that if we stretch it or pull it, then there will be a restoring force. That means the spring will pull us back in opposite direction. So if we are putting a force F in the right side, the spring will also pull us back with a restoring force. And this restoring force is proportional to your displacement. The more will displace, the more will pull, the more will be the restoring force. It's proportional to your minus x because it's in opposite direction, and we can write that F restoring equal to minus kx. K is your spring constant or proportionality constant. So this is your spring constant. Now we know that this force equal to also mass into acceleration, or we can write that this restoring force is m d square x dt square equal to minus kx, or you can simply write this is your acceleration, basically d square x dt square is equal to minus k upon m x. This minus k upon m can consider this is your omega square. So we'll write this your d square x by dt square is equal to minus omega square x. So if your acceleration is proportional to the negative of the displacement, then we can say this oscillation is in simple harmonic motion. So now this is a simple spring case. If we'll connect more springs which is having a different spring constant, we'll combine them in series or parallelly and will attach a mass to it. So what will be the net spring constant? So for that, first case we'll discuss is the parallel case. So parallel case we'll discuss like this. If springs are there, basically two springs will check, and you can connect n number of springs and both are connected to a single mass, let's say m. So as the springs are different, maybe one spring is of aluminum, another spring of copper or any alloy of new metal. So let's say that spring constant is k1 and k2. When I'll pull this mass in, both will expand and they will expand same because the same mass I am pulling, and both will have your here it will have a different restoring force, and for this spring it will have also a different restoring force, but the extension will be same as I am pulling this object horizontally. So what I can write, the force on this, suppose it is very soft, its force will be less, and but the extension for both this is both the your spring is same. So what we can write, we can write that the restoring force, let's say F1 for this spring 1, it is minus k1x. Displacement will be same for, because suppose if I am pulling and it is here, so displacement is same x for both the spring, but their k are different, so they will have different force on them. So it will have F2 which we will have K2x. Now as I am pulling and both the restoring force are in same direction, so the net restoring force by both the spring, we can say net restoring force or total is F1 plus F2, which you can say F1 is, I can take minus common, x also common, so K1 plus K2 x. Now if net means, let's say the combined spring strength is your K net, that is your spring constant, net spring constant. So if net I can write is K net spring constant into displacement is same, right, x. So what I can consider is my net spring constant or total spring constant is K1 plus K2 if springs are connected parallelly in having different spring constant. Remember, like your resistor, if we are connected in parallel, it's 1 upon R equivalent equal to 1 upon R plus 1 upon R2. But if springs are connected parallelly, then it's like a series connection in resistor, R1 plus R2, if resistors are connected in series. So here K net is equal to K1 plus K2. Fine. So how will you calculate the time period of combined oscillation? Now individual oscillation you can calculate for similar case. The time period you can calculate. Time period is basically, you will find that it is 2 pi, your omega is basically 2 pi by t. So time period is 2 pi by omega. Here your omega is, we have taken omega square is k by m, so omega equal to k by m root over. So omega is the denominator, so m will go up and k will be in the denominator. So you can write that your time period for single mass attached to a spring T will become your 2 pi omega in denominator, so it's m by k. This is your time period for single mass attached to a single spring. Now double spring parallelly connected, your k has modified to k1 plus k2. Now your time period for this type of modified springs connected in parallel or combination of springs, the time period will be 2 pi. The k will be modified, same mass is connected to both, so it will be k1 plus k2 instead of only k, it will come k of m by k1 plus k2. Fine. Now we'll discuss the case of your series. So if resistors, your springs are connected in series, let's say end to end, one spring, then another spring, then the mass is connected m. Let's say this is the spring constant k1 and this is the spring constant k2. So how you will apply the force? On both the springs, same force will be there, same restoring force, because you are applying force, let's say F to the right, same restoring force F will be to the left. So as both the spring are in the same, means so both the springs are connected end to end, so restoring force will be both restoring force will be same. So let's say the restoring force F I'm writing for both the springs 1 and 2 same, so F will become your minus K1, but as their spring constant is different, so they will expand differently. let's say K1 is spring 1 is expanded to x1 and spring 2 is expanding to x2. Their expansion will be different. So let's say the force and its expansion will be, it is expanding x1. I am applying force F to the right side. There is a restoring force Fs, let's say. So same Fs will also equal to K2 x2. So from here you can write x1 equal to minus F by K1 and your x2 is equal to minus F by K2. Fine. So now what I'll do, the net expansion will become your sum of x1 plus x2, because the total, this is expanding x1, this is expanding, let's say, x2. So the total expansion will be x1 plus x2. So the total expansion is x1 plus x2, which you can say minus F common, that is 1 upon K1 plus 1 upon K2, right? 1 upon K1 plus 1 upon K2. So you can write that x1 plus x2 equal to this one. If I'll write, that is minus F, so this is K1 K2, numerator K1 plus K2. So K1 plus K2, LCM K1 K2. If we'll write F equal to, minus sign will come this side and it will be reverse, like cross multiplication. So K1 K2 by K1 plus K2 and x1 plus x2. Now x1 plus x2 is the total your expansion. So F is proportional to the expansion minus of negative proportion expansion. So what is this? This is the equivalent. If you compare with the standard form, that is if s equal to minus kx, so this is, let's say, net your spring constant. K is the net spring constant and x is the net displacement. So if we compare with the net force by both your spring constant by the combination of two springs in series. So what you will do, this will be your net spring constant and this will be your net displacement. So your total, if you compare with this original equation, so your K net spring constant or total spring constant of this combination will become K1 K2 by K1 plus K2. So remember one thing, if springs are connected parallelly, it is K1 plus K2 simply combinations. If springs are connected in series, then the spring constant is K1 K2 by K1 plus K2. This is like series is like the resistor in, you can say, parallel, and parallel is like resistor in series. So you can calculate your, find out your time period. This is time period for parallel case, and for series the time period will become 2 pi m by k. K is this one, so by means K1 K2, K1 plus K2 will go up, so m into K1 plus K2 by K1 K2 under root. Fine. So this is for series. So in this video, what we have discussed if the mass which attached to a spring, if it will oscillate, if it is a single one, then it will of course execute the simple harmonic, or it will oscillate like simple harmonic motion, and its time period will be 2 pi m by k. Now If the springs are connected to more than one springs are there combined, two springs are there, then we'll get, if they are connected parallel, then your combined constant or net constant by these two springs will be K1 plus K2, and if this is connected series end to end, then the net spring constants will be K1 K2 upon K1 plus K2. Now from our equation, the time period equal to 2 pi into m by k, so putting the value of k for the series combination, that is K1 K2 by K1 plus K2, will get m k 2 pi under root m K1 plus K2 by K1 plus K1 K2. So these things we derived today. I think it's clear. Now one thing you remember, if this mass will hang like this, then also similar result you will get. This one you can try. If you require the help, you can write in the comment box, so that I'll make another video. If two springs are connected and one mass is hanging parallelly, then also you will get this type of result. And also similar thing, if both the springs are connected end to end and it is hanging, this mass is hanging, then also you will get the same result. So whether it is vertically hanging or it is oscillating horizontally, this result will be applicable. So thank you for watching the video. See you in another one. Bye bye.